Hello guys, welcome back to another video of Computer Vision with PyTorch series. In today's video, we'll be creating another model where we'll be adding non-linearity functions. So if you look at our previous video, we created a model which had model loss of 0.47 and had accuracy about 83%. So in today's video, what we'll be doing is we'll be adding non-linearity activation function and we'll try to decrease the model loss and then try to increase model accuracy. So if you haven't watched my previous videos, I highly recommend you to watch those videos and continue with this video because this video is the continuation from my previous video. So let us quickly recap what we did in our previous videos. So in our first video, what we did was we imported fashion-MNIST dataset and then we visualized our dataset using matplotlib, and also we created train and test data loader. We created train and test data loader because we cannot send 60,000 MS tensors directly to our model because it will be memory inefficient. So to solve that problem, what we did was we divided our images in batches. So in one batch, there were 32 images. So instead of sending 60,000 images to our model, we're sending 32 images, which will solve the problem of memory inefficiency. So after doing that, we created our baseline model. So we created a simple model where we had linear layers and the model outcome was the model loss was 0.477 and the model accuracy was 83%. So in today's video, let us create another model and try to decrease this loss and increase the model accuracy. So what we'll be doing in today's video is that we'll be adding non-linear functions. That will be the main aim of the video. So let us create another model. So we'll be creating model by using nn.module class. So if you haven't watched my previous videos, I highly recommend you to watch those videos and carry on with this video. So fashion. So let us name our model as fashion-MNIST vision model v1, and then we need to use nn.module class because from this class we get access to different linear layers and different activation functions. So let us create constructor def init, and then we need a self parameter, and we need several other parameters like input shape, and input shape is going to be of type integer. Also we need hidden units, which is going to be of type integer, and then we need output shape, which is going to be of type integer again. So let us call the constructor of superclass. So calling the superclass, and then let us call the constructor. So let us create our first model of the video. So let us create a stacked layer. So self.stacked layer, and now I'm going to create a sequential layer. Sequential. So inside sequential layer, I'll be creating several layers. So what sequential layer will do is that it will run all the layers that are inside this layer. So let us create our first layer. Our first layer is going to be flattened layer. Why we are creating flattened layer? It is because our images are 3-dimensional or 4-dimensional if there is bad size. But the problem is that our model cannot accept 4 dimensions. So to convert into 1 dimension, we are using flatten. I have discussed that plenty of times in my previous videos. So we created a flattened layer. Now what we need to do is we need to create an input layer. So we'll create a linear layer, and then in features will be our input shape that we pass while we are instantiating this class. So input shape, and then let us define out features. So out features is going to be hidden unit. So let us name this as hidden units. Hidden units. So after doing this, now comes the important part and comes different part. So we've created our linear layer. Now what we need to do is we need to learn non-linear patterns in our images. So to learn non-linear patterns, we'll be using ReLU activation function. So if you come to your new tab and search for ReLU layer, so what does ReLU layer do? So you can see ReLU layer provides non-linearity to the model for better computation performance. So let us use ReLU function. Let us learn non-linear patterns in our images, and let's see whether we can decrease the model loss and increase the model accuracy. So let us use our ReLU function. So after using ReLU function, now let us create another hidden layer. So nn.linear So in features should be the output of the previous layer, which is hidden units. So hidden units, and also we need to specify out features. So out features is going to be hidden units again. So again, let us learn nonlinear patterns by using nn.ReLU. So let us create our output layer now. So nn.linear. So again, in features should be the number of output from the previous layer, which is hidden units again. And now we need out features. So out features. So out features is going to be my output shape that I pass when I'm instantiating this class. So this was all. So we are using nn.module class. So we also need to create forward method. So let us create forward method. So def forward and self parameter, and then we need our data. So we'll be passing this data while we are training or testing our model. So let us return self.stacked layer, and let us pass data to the stack layer. So what we are doing is, when we call our model, or when we are training or testing our model, we'll be passing data to this layer. So first of all, my data will go through flatten layer, then to int layer, then to ReLU, where it will learn nonlinear patterns, then it will go to linear layer again, then it will go to ReLU, and then finally it will go to linear layer. So that is the meaning of sequential. All the layers inside my sequential layer will run sequentially. So let us run this layer. So now let us instantiate this class and create our model. So model 1. So let us instantiate the model. So fashion MNIST model v1. Yes. So let us pass our parameters. So first of all, let us pass input shape. Input shape is going to be 28 times 28. Why we are passing 28 times 28? Because when we invoke our model, when we pass data to our model, flatten layer will, create one dimension. So in our case, the dimension of our image is, let us see the dimension. So you see, we have 4-dimensional images that we pass through our model. So when we convert this into one dimension, it will be 28 times 28, which will be 700 something nodes. So we need to pass input shape as 28 times 28, because this parameter is being used as the input feature or in features for this layer. So the nodes should match the output of the previous layer. So that is why we're sending 28 times 28. So we also need to pass hidden units. So let us keep 10 nodes in our hidden layer. And also we need to pass output shape. So output shape is going to be length of my class names. And let us send our model to device. So why length is class names? Because we want our model to give probabilities, 10 different probabilities. So in fashion MNIST dataset, we have 10 different images. So we want our model to give probabilities of 10 different images. So we have created our model. We have passed our model to the target device. Now let us put our model parameters also to the target device. So next, model1 dot parameters. So by doing dot parameters, I get access to model parameter, and then I'll send my model parameters to the target device. Let us run this cell. Okay. So let us see model parameters. So let us visualize the model parameters. So model1 dot parameters. Shift enter. We can see the model parameters, and obviously the model parameters in the beginning is going to be random. So because our model is not trained yet. So now what we want to do is we want to set up loss function and optimizer. So let us set loss function and optimizer. So let us comment this loss function and optimizer. So let us create our loss function and optimizer. So the loss function we'll be using is nn.cross entropy loss. Why we're using cross entropy loss? Because cross entropy loss is used for multi-class classification problems, and we are dealing with multi-class classification problems. So cross entropy loss will internally apply softmax function, and then it will calculate the loss. So if you don't understand how softmax function works, I have already taught that in my previous video. So basically what softmax does is, initially my model will give me logits. So I need to change that logits to probabilities. So to convert the logits to probabilities, we need softmax activation function. So cross entropy function automatically applies softmax activation function and then we'll calculate the loss. So we're calculating the loss to understand how bad our model predicts. So we have set up our loss function. Now let us set our optimizer. So torch.optim. We'll be using stochastic gradient descent, and in this method we'll be passing model parameters. So model1.parameters, and then we need to specify the learning rate, which 0.1 is suitable. So let us run this cell, and we have set our loss function and optimizer. Now what we want to do is we want to train and test our model. So we need to create train and test loop, but this time we're going to do a little smart way. So before we create a train and test loop again and again, so to reduce that problem, we'll be creating a function so that we can use this function later on and not write the code again and again. So let us create a function for our training and testing loop. So first of all, let us create a function for training the model. So function for training the model. I'll also provide this code in the description so you can access it. So let us create function for training model. So train model will be, so we will need some parameters. So first of all, which model we want to train. So we will accept that using module parameter, and the type of model is going to be nn.module. So another thing we need is we need a data loader. So we need the data. So basically to train the model, we need the data, right? So this data loader is batches. So in one batch, we have 32 image along with this label, along with their labels. So we want data loader also. So torch.utils.data.data loader. Now what we need, another thing, we need loss function. So loss function is going to be of type torch.nn.module. Now another thing we need is optimizer, obviously. So torch.optim.optimizer, and we need accuracy function. So we have already created accuracy function. So accuracy function is our custom function that we created. So what this does is that it will return the accuracy of our model in percentage. So another thing we need is device, which is going to be of type torch.device. So let us come inside our function and let us create a docstring. So this function trains the model. Okay, so let us create our training code. So first of all, what we need to do is, so let us comment. So first of all, what you need to do is we need to set our model in training mode. So to set our training mode, so we need to do model.train. So now what we need to do is let us define two variables. So first of all, we need train loss, and another thing we want to calculate train accuracy. So both will be initialized to 0, 0 at the beginning. So we have our data loader. In our data loader, there are 32 images. So basically data loader are batches. So in our training data loader, we have around 1800 something batches, and in each batch we have 32 image. So we need to loop through each batch. So to loop through each batch, let us write our loop statement. So for each batch, and we need xtrain, ytrain. So when we enumerate through our data loader, so enumerate data loader will return the batch number, and then it will return xtrain and ytrain. So in the first loop, what will happen is the batch should be 1, xtrain will have 32 image features, and then ytrain will have 32 image labels. So let us create a device agnostic code so that we don't get device mismatch errors. So device agnostic code. So we need to send xtrain and ytrain to the target device. In our case, the target device is CPU, but in your case, the target device might be CUDA or even CPU. So xtrain dot to target device, and we also need to pass our ytrain to the target device. So okay, now let us do forward propagation. Second step is forward pass. So we need to pass our X train through the model, and as I told you, our model will return logits, and it is our job to convert logits to probabilities by using softmax function. But since we are using cross entropy loss function, we don't need to convert that to probabilities. So our model will return logits. So let us store that in the function or in the variable ytrain logits. Now, third thing what we need to do is we need to calculate the loss and accuracy. So third step, calculate the loss and accuracy. So loss is going to be, we need to invoke our loss function, which will calculate loss for us, loss. So in our loss function, we need to pass logits. So ytrain logits. Okay, also we need to pass the actual label. So actual label for x train is ytrain. So our loss function will internally convert logits to probabilities, and then it will compare each probability with ytrain, and then it will calculate how bad our model performed. So for each batch, let us sum our, so we have train loss, and we will add each loss for each batch. So similarly, let us calculate accuracy. So accuracy equals to, we have created our accuracy function, which accepts two parameters. One is ytrue, so we need to pass actual value, which is ytrain, and another thing we need to pass is ypred, which is, so our ypred accepts like the probabilities. So in this case, we need to convert ytrain logits to probabilities. So to convert ytrain logits to probabilities, what we'll be doing is we will be getting the maximum number, and we'll be getting the index of that maximum number. So this will calculate me the accuracy. Now I need to calculate train accuracy by adding all accuracy across all batch. So this will give me the sum of all accuracy. So fourth step, what I need to do is I need to set optimizer to 0 grad, optimizer 0 grad. So why we're doing this step is because in each backward propagation, the optimizer will be accumulated. So before doing next backward pass, we need to clear out the optimizers. So optimizer dot 0 grad. Again, if you find difficult for understanding these concepts, I've already discussed that in my previous videos. I highly recommend you to watch those videos. Now, fifth step is backward propagation. So in fifth step, what we'll be doing is, okay, so we'll be doing back pass, so loss dot backward. So, and the final step, what we'll be doing is optimizer step. So in this, we'll be changing our model parameters. So basically, we're improving our model parameters so that we get accurate output. So in train loss, we have the total sum of all the loss across all batch. In train accuracy, we have total sum of all accuracy across all batch. So let us calculate average train accuracy and test train loss. So we come one step outside of our batch function, and then what we need to do is we need to divide our train loss by the length of our data loader, which will give us the average train loss, and similarly divide train accuracy with the length of our data loader, which will give us average train accuracy. So train loss is equals to, so divide equals to length of our data loader, which is going to be data loader, and then train accuracy divide equals to length of our data loader. So this will give us the average train loss and train accuracy. And for each batch, what I want to do is I want to print the train loss. So not for each batch, but when we invoke our train model. So first of all, train loss. So let us print train loss. Train loss is in the variable train loss, And then another thing I need to print is train accuracy. Train accuracy. Okay, we've created our train loop. So next time we can just invoke this loop, invoke this function, we can pass these parameters and train any model. So let us run this code. Okay, so since we have created training loop, in the similar way, let us quickly create our testing loop. So testing function, what I mean. So function for testing the model. So it is going to be very similar to what we did here, but in this case, what we want to do is we need to test our model by passing xtest, and we want to evaluate the model. So def test model. So again, I need to accept several parameters like model, which is going to be of type nn.module. We need a data loader. In this case, we'll be passing test data loader. So torch.utils data loader. And another thing we need to pass is loss function. So which is going to be of type torch.nn.module. Torch.nn.module. And what we need to pass is we need to pass accuracy function. Also, we need to pass the target device, which is of type torch.device. So let us create the testing loop. So again, let us build a good habit by writing docstring. So this function returns the training model results. Testing model results. Okay, testing model results. So let us write code for testing our model. So it is very similar to what we did in our train function. So first of all, let us define or initialize two variables, test loss and test accuracy to 0, 0. And then we need to set our model to evaluation mode. And then what we need to do is we need to define context manager, which is torch.inference mode. So inside this, we need to loop through every batch. So in our train data or test data loader, we have around 313 13 batches. So we need to loop through each batch. So for each batch, we will get x test and y test in enumerate data loader. So okay, so enumerate data loader will give me every batch number, and then it will give me x test and y test. So x test will have 32 image features and y test will have 32 image labels. So first of all, good practice is to send our data to the target device. So x test dot to target device, and similarly we need to pass y test to the target device as well. So after doing this, what we need to do is we need to do forward pass. So first step is forward pass. So forward pass. So let us call our model and then pass x test. So our model will give us logits. So let us store that in the variable y test logits. Now we need to calculate loss and accuracy. So second step is calculate loss and accuracy. So we will store loss in loss variable. So to calculate the loss, we need to call our loss function, which is cross entropy loss. So cross entropy loss accepts y test logits and then the actual value, which is y test. So let us add all the loss from each batch and then store in the variable test loss. And similarly, we need to calculate test accuracy. So test accuracy, we can add each accuracy and we'll call accuracy function. We'll pass the actual value. The actual value is y test. And then the predicted value is, so our accuracy function is expecting, probabilities. So we need to convert logits to probabilities. So to do that, what we'll do is, so y test logits, and we'll find the number which has the maximum probability and we'll return the index of that position. So argmax and dimension equals to 1. So we have calculated our loss function or loss and accuracy. So similar to what we did in our train function, we need to calculate average test loss and average test accuracy. So we will divide our test loss with the length of data loader, and similarly we'll divide test accuracy with the length of data loader. So test loss divide equals to, so length of our data loader. Similarly, test accuracy is going to be length of data loader. So test accuracy equals to test accuracy divided by length of data loader. So let us print some information. So print statement. So we want to see test loss. So test loss, and similarly we want to print test accuracy, which is in the variable test accuracy. So let us run our cell. So our cell has run successfully. So now what we need to do is we need to train and test our model. We have already created train and test functions, so this will make it very easy for us. So let us set a manual seed for reproducibility. So manual seed, let us put 42, which is a good number. So let us do timer. So this will give me the start time. So I want to train my data train my model for 3 epochs. And now let us create a loop for each epoch. So for each epoch in TQDM, so TQDM is used for progress bar. So for each epochs, so let us add a print statement. So print, okay, I mistakenly run the cell. So print, so we want to see which epoch we are currently on. So epoch, and then \n, which will give me the next line. So I want to train my model. So let us call the model that we just created, or function that we just created, train model, and we need to pass our model. So the model we created was model 1. So we created model 1, right? Or am I? Okay, yes, we created model 1. So we've passed model equals to model 1, and then similarly we need to pass data loader. So we want to train our model, so let us pass train data loader. So train data loader has around 1875 batches, and then another thing we need to pass is loss function. So loss function is our loss function, which we created in the above cells. So another thing we need to pass is optimizer equals to optimizer, and then we need to pass accuracy function. So accuracy function equals to accuracy function, and last thing we need to pass is our target device. So device equals to device. So in similar way, let us also call our test model. So this function will test our model. So model equals to model 1. So model equals to model 1, and then we need to pass data loader. So data loader will be test data loader this time, because we are testing our model. So to test our model, we need to send test data. So our test data loader has around 313 batches. So another thing we need to pass is loss function. So loss function equals to loss function. We also need to pass accuracy function. So accuracy function equals to accuracy function, and then we need to pass our target device. So we have our start time. So let us also define end time. So why we're doing this start time and end time is because we want to calculate how long it took for our model to train and test. So we have a function called print train time, which we created in our previous videos. So this function will return me the how long actually it took to train my model. So we'll pass start time and end time, and it will calculate the difference and it will return the print statement. So start equals to start time, and then end equals to end time, and then finally we need to pass device. So let us run this cell and let us see how long it takes for our model to train and test, and then we'll also visualize our training and test. So let us run this cell. Okay, we can see our print statements. So we have successfully run all the epochs. We can see a nice progress bar, which was created by TQDM, and we can see in first epoch the train loss was 0.69, and as the epochs go on, in the third epoch the train loss went down up to 0.45. Not good, but our model is learning nonlinear patterns. And again, test loss was in first epoch, the test loss was 0.52. In second epoch, it was 0.50. And finally, in third epoch, test loss was 0.48. And let us also see accuracy. So accuracy also seems to be going up. So overall, our model seems to be learning, but not that much. And finally, the train time on CPU, which is our target device, is 29 seconds. So it took 29 seconds to train and test our model. So let us evaluate our model. So we have already created a function called evaluate model. Evaluate model. In evaluate model, we need to pass our model, which is model 1. We need to pass test data loader. Test data loader equals to test data loader, and then we need to pass loss function. Loss function equals to loss function, and then we need to pass accuracy function. So accuracy function equals to accuracy function, and also let us store the result in model 1 results. So model 1 results. So okay, so let us view model 1 results. Okay, we can see our model name is Fashion MNest model V1. The model loss is 0.48. So it's 48% loss. So our model is doing as good as guessing. The model accuracy is 82%. So let us also see the model 0 results, which we created in our previous videos. And let us compare the results from these two models. So model 0 had 0.47 loss, and actually model 1 has greater loss. So looks like our model 0 is bad than model 0, and the accuracy also seems to be low than our previous model. So our model is able to learn non-linear patterns, but again, it's not better than our previous model. So looks like we have a missing piece, and the missing piece is that we need, for training our images and to learn patterns in our images, we need to create convolution neural network. We cannot use traditional neural networks like we just created. But again, why we created these models? It is because we needed to understand why this model didn't work. Understanding why model works is as important as understanding why the model did not work. In our previous video, we created a model where we just had linear layers, where we just tried to learn linear patterns. The model didn't do well. So in today's video, what we did, we created a model with nonlinear activation functions. So we tried to add nonlinear activation function like ReLU, and finally we evaluated our model and we visualized that our model was even bad than the first one. So with this, we know that there is a missing piece, which is we need to create a special neural network called convolution neural network. So this process was very, very important. So in our next video, what we'll do is we'll create convolution neural network. And if you need to access this code, I will provide it in the description. Also, I promise creating these two models was very, very important, and this everything that we've learned will connect in our previous videos. So that is the reason why we created two models and we created them in the separate videos. So subscribe to the channel, like the video, and let me know in the comments if you have any confusion. In the next video, we'll be creating a special neural network, which is convolution neural network. Thank you.